So Newton's laws, okay? So a force, they defined a force in the video, right? It's either a push or pull on an object, okay? It's a vector, so it has magnitude and direction. Requires something that does the pushing or pulling, okay? And either a constant force or force that acts on an object by touching, or a long range force. Gravity would be an example of that, okay? So there's like, not constant force. I don't think this is supposed to say constant. It's supposed to be contact force, sorry. Must have just typed it wrong and the and Word corrected it on me. It's a contact force. That comes when you actually touch the object, contact, right? And then you have long range forces, which would be something like gravity, right? Where it's acting on you from a long range, okay? And then we saw that Newton's first law was the law of inertia, right? Which basically says an object in motion will want to stay in motion, okay? And an object at rest will want to stay at rest, okay? So consider an object with that no force acting on it. If it's at rest, it will remain at rest. Rest. And if it's moving, it will continue to move. Okay? That's like the hockey puck example, right? If there was no friction on the ice and you you apply a force with the stick, right? It's going to continue to move, right? Until such time that the ice gets rough enough that there's enough friction to slow it down, right? Newton's second law is the one we were trying to get to this morning. An object's mass m, subject to forces F1, F2, F3, will undergo an acceleration. Right? And so we talked about this morning, if the sum of the forces acting on whatever object is not equal to 0, then you're going to see some motion, a motion in the form of acceleration of that object, right? And so we saw acceleration. I want to write, I want to write it F net equals ma, okay? Okay, and the acceleration points in the same direction as the F net vector, okay? So keep in mind, we could have a question that does something like this, right? Where we have a force in the x and we have a force in the y, and this is the F net vector that they are referring to, right? So you get this net force acting in this direction, but with it, what this is saying is that the acceleration also occurs in that direction, okay? Okay, it happens, and you can figure that out with the angle. And if it was an easy question like this, Pythagorean and SOHCAHTOA trig, right? So for instance, here I'll draw another free body diagram here, just as an example. We'll have some mass m sitting by itself here, and we're going to have typically all the forces acted on the center of the object. Right, we're going to have Fg. You guys could try and be as precise as you can. So if you know that two forces are going to be equal, try to draw the arrows equal, the vector, try to draw them in equal magnitude, right? Because their relative size, that would be a much bigger vector than this one. Okay, not that I'm going to be overly picky on something like that, but let's just keep that in mind, right? If a force vector appears to be bigger, then you should expect to see its magnitude bigger, okay? And then we could have, like, let's say an applied force, right? Something like this, Fa, and we could have, I don't know, the force of friction or something opposing the motion. right? All vectors. Anybody have any questions? When I add all these things up, if they don't equal 0, it means the object is moving. And so I can find what that acceleration is going to be. Right? Okay. And Newton's third law stated that every force occurs as a member of an action-reaction. Action-reaction pair, okay? The members of an action-reaction pair point in opposite directions. Right? So an action-reaction pair, they have point in opposite directions with equal magnitude. All right, that's right there, equal magnitude. Okay. And I think an example like this morning, if I just think back to this morning's example, this is kind of I'll just reiterate it here. Like a box sitting on a counter or something, right? You have its weight, and its weight we just learned as being Fg, right? That's the weight. And the reason why it doesn't crash through the table is because Fn is equal and opposite. Okay, this will be an action-reaction pair, Fn and Fg. Okay? Everybody okay? Okay, so what I want to do here, I just want to show you guys, like, I just finished, like, somebody dropped in for some office hours, and I showed the like where we could apply something like dimensional analysis, right? And that helps me lock in particular concepts, right? It's dimensional analysis. So what we want to do here is I want to figure out what the dimensions are going to be for force, right? I've already told you, like, we already know the units for force are going to be in newtons, right? Which we denote as an N. But what is a newton? That's what we're after. Like, what does that look like? Okay. And so when I do the dimensional analysis on this, like I want to know what are the units, right, for force. Well, if I look at what force is equal to, I know that mass is measured in typically kilograms, right? And when I multiply kilograms by acceleration, we know acceleration is meters per second squared. So what do I get as my units? I get something weird that looks like this. Well, we know that force is measured in newtons. Well, that just means that this 1 kilogram meter per second squared is equal to 1 newton. 1 newton is the acceleration of a mass. Okay. Anybody have any questions before I move on? There's a couple times I came up in university, right? And if you don't have a clear understanding as to, like, sometimes where like something like a newton came from, they like to throw these like weird units into answers and things, and you're like, I don't know what that is. It's just you might not always know what it is, but you can apply dimensional analysis based on some of the equations that you know, right? Like, we know that force is measured in newtons from this morning. We also know that F net equals ma. Well, that's where the units come from, right? They just want, again, everybody, mathematicians and people in physics are lazy, right? We don't want to write this every time we write an answer, right? Physicists like newtons. Short and sweet. Okay, easier to conceptualize, I think. So here we go. I'm going to run you through 3 examples and then we're done. Okay. Again, nicely scaffolded for you. Part A, Part B. So a curler exerts an average force of 9.5 newtons south on a 20 kilogram stone. Assume the ice is frictionless. The stone started from rest and it was in contact with the girl's hand for 1.86 seconds. Okay, so determine the average acceleration of the stone. Okay, that's where we're at. Okay, so I sometimes just like drawing my pictures, right? I got like kind of my ice surface here. The thing with the free body diagrams is it kind of gives you, I don't know, it gets like puts words into a picture and kind of like allows you to kind of see what's going on, right? So it tells us that the curler exerted an average force. We'll call this in the south direction. North will be in the negative direction this time, right? You guys have the freedom to do whatever you want. I think for this particular question, saying that this is the south direction, it just makes it easier to be positive. Okay. So we know that the force here is 9.5 newtons. And we know the mass is 20 kilograms. Okay, so assume the ice is frictionless. So what's the first part? We're average acceleration. Okay, well, I have F net. The only force acting on this, it told me that it was frictionless, right? And aside from, you know, it's going to have its weight, and it's also going to have Fn, but those two are going to cancel each other, right? And so really F net is only being affected by this force acting in the x direction. So I know that F net equals ma, right? And I also know that the only force, the only imbalance in the force is in the x direction, right? And so I know that this is the only force. 9.5 has to equal 20 times the acceleration. And so the acceleration, or the average acceleration of this stone should be, what did I get? 0.45, 0.475 meters per second squared. Does anybody have any objections? What just happened there? Okay, this would be a, I was also saying at the office hours, like some of the harder questions here, like determine the velocity, they don't tell you to do this, right? And so that's where the questions get a little bit more difficult. It's like, it's a puzzle, right? And so we have to be able to like navigate to the final answer by looking at some of the information that's given to us and what we can find and then use for the second part of the question, right? So part B here, determine the velocity of the stone when the curler releases it, right? We know that it's in the curler's hand for 1.86 seconds, right? We also know the acceleration. We also know, so what are we doing? We're writing down all the things that we know and we don't know, right? We know t equals 1.86. We know a is equal to 0.475. And we know B1 started from rest. What are we asked for? The velocity of the stone, V2. All right, so you just pick a kinematic equation. This is connecting it for you, right? Well, you could say VF is equal to, well, you guys can go to your formula sheet too, right? Actually, it's a good opportunity. Did everybody see that I posted the formula sheets here? So you can open this up. This is a front back kind of formula sheet. You go here and you can find you find your equations here. Okay. Well, it looks like I'm going to pick this one, right? Because I know t and I know acceleration and I know the initial velocity and I'm interested in the final velocity. So I'm going to go VF is equal to VI plus AT. Right? I know I'm interchanging. So I told you guys I do this. VI and VF, the same things. V initial, V final. Right? We know VI is 0, so VF is going to be equal to the acceleration times how long it took to get there, right? So you just plug in the numbers. 0.475 times 1.86. We should get 0.884 meters per second. Sorry, meters per second. South. Don't forget your directions. This is a vector. Any questions? I know I got rid of the chat here. Okay. There's no questions with that. We'll jump down to the elevator question. Okay. A man is riding in an elevator. The combined mass of the man and the elevator is 700 kilograms. Okay. Calculate the magnitude and direction of the elevator's acceleration if the tension in the supporting cable is 7,500 newtons. Okay. I want to draw a picture. You're just going to draw a box. This is my elevator, and I got a little guy standing in there, right? And we're going to have a rope of some kind or a cable with some tension in it, force of tension, and it's going to be positive, acting in the positive direction, right? And then I'm also going to have, should go from the middle, the weight, Fg, which told us, well, Fg is mass times gravity, right? And it told us what the mass of the elevator was with the person inside, right? M was equal to 700 kgs. Okay, so we can figure out what Fg is. Fg is the mass, 700, times 9.8, negative 9.8. I put the negative in here with the forces to always remind myself that it's acting. My answer is going to come out negative. And that's going to always prompt me that it's acting in the negative direction. So that when I sum the forces, there's a little bit less thought there, right? You're just going to go, well, we'll see that in a minute. But the negative always keeps me in line with the fact that it's acting in the negative direction. Okay? So Fg is equal to, what should we get? 6,060 newtons. Okay, and when we saw the tension in the top was 7,500 newtons. So now, there are no forces in an elevator that I'm aware of acting in the x direction unless there's like some stabilizing somehow, right? So that it doesn't go side to side. That was horrible. Side to side. Okay, so the only forces acting in this question are forces in the y direction. All right, so you're going to get, okay, well, the sum of the forces in the y has to equal the mass times the acceleration. What are the forces acting in the y? We're going to add them up. Well, I see one here and one here. So we're going to say, okay, we're going to have positive force of tension, which you guys could actually just, you don't need the Ft, you can go F, you can just go capital T, sorry, for tension. How you choose to, like, what's the word I'm looking for? Denote, and that's not the word. Label each of these forces is up to you guys. I'm just giving you the most typical. Like T is, that's typically tension. Force of gravity is always minus Fg pretty much, right? And that has to be equal to M times A. Right? And you'll notice the negatives on there, right? Because it's acting in the downward direction. And silly me didn't put the negative on the answer. Okay? So I suppose you don't want to do, you want to be careful, I guess. Now I'm just thinking. be careful with, like, if you're going to make the number negative, then the number's going to stay negative. If you guys just want to treat A as just being 9.8 and your number's going to come out positive, then you're just going to look at this and say, okay, well, FG's acting in the negative direction, so I'm going to make it negative. If you don't want to worry about the negative sign. Okay? Either or will do. Just be careful that, like, you don't do this in the next step. Don't do this. If you do include the negative, and maybe you guys don't want to do the negative on the 9.8, that's a problem, because that's going to cancel now and you guys are going to get wrong answers. Okay? So pick one or the other. If it was me, I might choose, now that I've actually had a thought here, to leave the negative off. And just know that the force of gravity is acting in the downward direction. So I throw the minus sign on there. Okay? And then you just plug in the values verbatim, right? So I know the force of tension is going to be 7,500 newtons, and that's positive, right? Minus the force of gravity of 6,860 is equal to, what's M? M was 700. You just solve. You do the math. Right? I think we get it's 640. Is that right? Okay, and then you just divide both sides by 700. And A will equal 0.914. Okay. Not exactly the answer, but very, very close. Okay. It came out to be positive. Oh, silly me. Look, I'm as bad as you guys are forgetting directions. Which direction is this thing moving? Is it going to move in the upward direction or the downward direction, right? It's going to move up, because you can see that the imbalance, the force in the positive direction is much greater, not much greater, but it's bigger than the force in the downward direction. So we got to be able to say up, north, something, okay? So I was getting that on the formative too. When you guys look at anytime you have a vector, you got to remember to put the magnitude and the direction. Okay. And then if you guys would like, you could just write a little therefore statement. Okay? Any questions? Got one more to do. Okay? This one's a little challenging. A little bit more challenging, okay? We know, okay, that F net, I always like writing this sometimes. Like, I'm like, F net equals the mass times the acceleration. This always, sometimes, like, just writing that down always, like, helps me with sometimes solving questions like this, right? And what are we doing? We're combining kinematics with forces now. Right? What force needs to be applied in order to reach these particular scenarios, okay? So the challenge here is, as I read this question, the cyclist increases her velocity from 6 meters per second east to 14 meters per second east. So let's just start writing things down as we read the question. We know initially she was going, VI was 6 meters per second east. So that's going to be positive. Okay, we'll set up our coordinate system in such a way that east is positive, north is positive, okay, and the other two are negative. Okay, and then we also know, oh, she got to 14 meters per second east. How long did that take? Well, 6 seconds. T equals 6 seconds. Okay, then it also tells us something else. It says, okay, well, the mass M equals 58 kg. Find the net force. In order for me to find the net force, and this is you guys, like, this is a puzzle, right? It's a puzzle physics is a big puzzle of like different pieces, right? So you have this one piece here, right? And it states that the net force, ultimately what it is we're looking for, net force, right? It wants to know what the net force acting in order for this particular set of data to come about, right? And so we know that F net is equal to the mass. Oh, great, they gave us the mass times the acceleration. Okay, but they gave us all this other information. But they didn't give us the acceleration. So now I'm like, okay, well, I need to find this. Well, how do I find that? Well, you use the other stuff. You use kinematics. So find what A is. Once you find what A is, you can plug it in here with this, and you find the net force. Okay? Any questions? That's what we're going to do now. Okay, so this is like, physics is cool from the standpoint that you get to like pull upon so much of, like, it's math. It's like math in the sense that like it just keeps adding up, right? You can pull on skills. Like everything we learn is a skill that you can use, right? And it's about applying those skills in certain situations, which is kind of cool. Okay, so let's find the acceleration. Let's pull up our formula sheet. We'll look at what we got. Okay, so I'm given VI, VF, and T. And I want to find A. Okay. Well, nothing about distance, right? Like, it doesn't tell us anything about distance. So we're kind of stuck with that. I don't really want to find anything with distance. Well, this looks all right again. Right? We know VF, we know VI, we know T. We just want to find A. So, okay, let's pick this equation. So we'll go VF is equal to VI plus AT. That looks pretty good. VF will be 14, and VI will be 6 plus A, that's the thing I want to know, times 6 seconds. So just solve for A. Create a zero pair, minus 6, minus 6. So 14 minus 6 is going to be 8. Right? And that's going to be equal to 6A. Divide both sides by 6. A will equal, I actually need my calculator for this one because I don't have the solution in front of me. 8 divided by 6, that should be 1 point something. 1.3. Okay, and that's going to be in the eastward direction. Right? Just to keep things consistent, okay, and then now what? Well, okay, well, we can take that answer that we just found. We can use just the acceleration. It's the same acceleration. We just want to know what force is the cyclist applying to the bicycle in order to allow for this acceleration to occur. All right, and so we say, okay, F net is equal to the 58 kilograms. Oh, this is a good opportunity. I'm going to write the units in here just for everybody, okay? 58 kilograms times 1.3 meters per second squared. Okay, so when we do the math on that, we're going to see, oh boy, 58 times 1.33, 77.14. Now take a look at the units. What do we do? Well, the units are going to be kilograms, meters per second squared. Well, this looks awfully familiar. That's 1 Newton. Right, so we say F net newtons in the east direction. Okay, is everybody okay?